Well, if there are any questions, if anything comes up, I'm happy to answer those questions right away, rather than wait until the end. But we'll see how it goes. So don't hesitate in asking or using that chat when you need to. So ESI started. We're 50 years old this year. Our firm this is our 50th anniversary. Started by a group of professors and graduate students at the University of Minnesota. What happened was during the Vietnam War, it was real unpopular for the professors and the consultants and the students at the University of Minnesota to consult with some of the manufacturers of military equipment. And so what the university did was they cut out all consulting entirely. It didn't matter if it was for medical devices or for bridges or for military stuff. They stopped all outside consulting. And so there were a group of professors and graduate students at the U that were consulting with structural firms to do computer analysis using the university's mainframes. And the analysis was on buildings and bridges, not military stuff. And that came to an end. So this group of structural firms from the upper Midwest pulled some money together and ESI spun off of that. And this picture is David Peterson. This is actually the basement of the structural engineering building at the University of Minnesota. And in front of him, you can see the ESI logo that we used for many, many years. And he's sitting at some terminal, no monitor. You can see the phone plugged into the side of it. And he's doing some programming of something. But that was 50 years ago. And here's another picture of Dave with Jack Hanley. Dave retired a bunch of years ago, but he still works 2 days a week here. So he was employee number one. So who we are today, we're still a very small consulting firm, and we still do work in the areas of structural dynamics. We still do a lot of analysis for some of those same structural firms that we did work for 50 years ago. But we also do a lot of work in noise control and acoustics, which Ryan does. We do a lot of work in vibration and vibration analysis, whether it's buildings or equipment and machines. And so we provide specialized engineering services to architects and engineers and manufacturers, facility owners, universities, hospitals, whoever, in those areas of structures, structural dynamics, noise, and vibration. In our projects, at times, we've worked on very, very small medical devices to cranes that carry nuclear waste. So the scale is real broad, but it's the same math, it's the same physics, many of the same problems, and it's fun. Every day is a new challenge. So what I'm going to show you today are 5 projects, and then just some examples, some photos of some bad isolation. The first ones are kind of unique. The next 3, these are grouped like this on purpose. These kind of go together. They talk about mechanical equipment vibration isolation. So let's just jump into the first one. A local A&E firm came to us and said their client wanted to put a go-kart track in the Mall of America here in Bloomington, Minnesota, on the 4th floor, not down in the basement on a slab that's on soil, but up on the 4th floor that was on other retail space, above other retail space, and near some real nice restaurants. And these aren't just go-karts that you putz around in. These go-karts go 50 miles an hour. They're very fast. With the person in it, I think the gross weight was maybe like 650 pounds for one of these go-karts. And so one of my first questions was, has this been done before? Where has this been done? And there was a place in India, in Mumbai, where they had it on an upper level floor go-kart track, and one in Barcelona. And 2 weeks later, I was here at this go-kart track in Barcelona, Spain, measuring noise and vibration from go-karts. And you can see this is very similar to what was built at the Mall of America you can see this is 2 levels. You can see the cart coming down this part of the track and then looping back around underneath that track. And that 2-level part of this was the big challenge. Again, here's the track in Barcelona. I don't know how well this is going to work, but I want to show you how fast these go-karts go. These were gas, gas engine powered go-karts. What we're putting in at the Mall of America were battery carts. So we'll see if this little video here works. Can you see the go-kart coming?
It's not streaming smoothly, but it started giving it to us in stop motion video. Exactly.
Now, you may not get a feel for how fast they are, but it's very, very fast.
What was the speed?
These carts can go, the battery powered ones could go up to 50 miles an hour in the straight sections of this track. So we actually got one of these go-karts. In addition to making a lot of measurements in Barcelona, we got one of the battery powered carts delivered to the Mall of America in some vacant space. We were able to drive it and make measurements there as well. And what we determined was that the floor, the 4th floor, the structural floor, you could not drive on that. There was not a way to control vibration going into that floor if you were driving on that floor. So what we did was helped the structural engineer. The structural engineer designed this, but we helped with the design. So the green here is the 4th floor at the Mall of America. The magenta color is the main level for the go-kart track. And then this is the 2nd level for the go-kart track. And the blue is the ramps going up and down. So you drive around down here, you come up, drive around this part of the track, go back down, come back around. It takes about 1 minute to go around the track one time. And in the photo, you can see the down arrow here. That's this down ramp right here. Yeah. So we did finite element analysis on this. What we found, this worked real well to keep the carts from not driving on the 4th floor was key. So the structure goes back to the building columns. But the bigger challenge was you've got a cart that's comes around a corner here at 20 miles an hour, it weighs 600 and something pounds, and the front wheels hit the ramp going up. And of course, if that's abrupt, you get high forces, but even if you make that a gradual slope, it's going fast enough that impulse force into the structure is too high. And we would get vibration back, we would get forces going back to the columns that would excite that 4th floor structure and other floors in the building. So we had to do something with these ramps to isolate, to reduce the magnitude of the impact force that was going back to the columns. And the way we ended up doing it was, here's another model of the of the structure. The green parts here, the ramps, are actually spring isolated. We actually put them on coil springs. So the lower part of the structure is stationary. The upper part of the structure that has metal deck and concrete is spring isolated. And the next photo, here you can see the springs in here. And that worked real well to reduce that impulsive force going back into the building. So this ran for a couple years, and it was a little less than 1 year ago. This It was called SMASH, SMAASH. It wasn't just a go-kart track. They had lots of other games and kind of interactive type simulators and things there. But they closed. So this sits vacant right now, unused. But it did work, and it was a very exciting project. And a good project for us to, control vibration back in this building.
Tony, how did you measure the vibration in the building? Like, so, like, do you use accelerometers? Do you, like,
Yes.
when you got that sample cart from Italy and did you drive it on that 4th floor and measure vibration?
Yep. We put it on, we drove it in a vacant area of the mall on a floor that was very similar, above some retail space, and used accelerometers and a multi-channel signal analyzer, a spectrum analyzer, and measured the vibration on the slab.
And that's how you could tell it was too high, like
Yep.
putting the part on the floor would produce too much vibrations.
Yep.
And then did you test it after you put these spring isolators in too then? Did you?
Yep, we made measurements on that 4th floor. And the biggest thing was nobody was complaining. They don't complain. Everything's good. So it was, the vibration was high enough when we drove it onto the floor before this was done, just in our testing, in that retail space down below. The ceiling grid was shaking. It was a fairly smooth floor, but the ceiling grid was shaking. There was some other display stuff where there were some kind of plastic plants and things in the leaves. You could just see the leaves shake. The lights were shaking, and you could hear the noise. There's not much for suspension in those go-karts. So all the motion that you have, that you feel in your body, it's pretty much going into the floor. There's no isolation, and the tires are not very soft. They're pretty stiff.
Can I also ask what FEA program you use to produce those?
For that, I think that is SAP 2000, which is a structural program that's been on for a long time. We have two or three different FEA programs we use here, depending on what the project is and what we're doing.
Do you have to calibrate this model at all? I know less about structural modeling and more about acoustic modeling, so I'm curious.
Well, yes, because we could go to the building. This floor, the green part here existed, and it was vacant. So we did go there ahead of time, and we did heel drops, measured natural frequencies of the building, of these bays, and then, but it's not too hard to put them all together. And if we go out and do a heel drop in a bay like that and find that the first mode, or one of the first modes of these bays are 6.5 hertz, it's not all that hard to put them all together and come in, and your first crack at it, you're at 6.25. You can do a pretty good job. So it was a lot of fun to drive these go-karts. This was a real hit.
Do you see the chat question there?
Pardon me?
Do you see the question in the chat? I'm happy to read it.
I don't see any chat questions, no.
Okay, there's a question that comes in. What was the natural period of the building?
Of that structural bay, as I recall, I think these were about 6.25 or 6.5 hertz was the natural frequency of these bays. We weren't too concerned about the entire building, as far as sway or anything like that. We're more worried about local vibration in these bays, and in the floors below. We went and measured those as well. All right, the next example is maybe not as exciting, but it's at the University of Minnesota, right on the main campus. A few years ago, they built, it was called the Physics and Nanotechnology Building. And it's a research building. And here in this area where where it was highlighted here, the dash circle, is a clean room for very, very sensitive equipment related to nanotechnology. And they're doing microelectronics research. There's some medical things that are going on in there, but all related to nanoscale type technology. And the challenge is here we have extremely sensitive to vibration. And we have some streets here on campus where we have trucks and bus traffic. This is a parking ramp right here, and lots of cars that are coming through here. A lot of buses coming down this Harvard Street. And right here is Washington Avenue. If you're at all familiar with the University of Minnesota, this is kind of the main, used to be before the light rail came in, used to be kind of the main road through the campus. But now we have trains. We have trains that come by there, and they're 1 block away. So lots of concern about vibration here. And clean rooms, very controlled temperature, humidity, particles, cleanliness, and also vibration. Here's a photo of just some of the equipment. This is not that clean room. It's the only one I had with people all gowned up, so I put it in there. But this is the physics and nano clean room, and I think this is a mass spectrometer. But this is some of the equipment that's in there for inspection. And this is I think it's electron beam lithography. So nanoscale gridding of some substrates for semiconductor type work. I mean, maybe there's some scales over here and microscopes back here. Some other sensitive things as well. So the first thing when we got involved with this project was to go and to make vibration measurements at the site. So down in the lower right corner, you can see the locations where we made initial measurements. And our criterion, I'll show you in a little slide coming up there, like we have NC curves for noise that you're probably familiar with. There are also things called VC curves, vibration criteria curves. And one of the lower levels that we work with is called VCE. And E is this magenta line right here. It's 125 microinches per second is the level. Usually defined between 1 and 80 hertz. This one extends out to 100. But in it, and we use 1/3 octave bands when we compare to VC curves. So what we're looking at here is narrowband vibration plotted on a log-log scale, and then the 1/3 octave band levels associated with that, with the same measurement. Up here is the time waveform, and you can see there's a transient that happened here around the 2-second point. But the ground, the soil out here from the traffic is 2 times here. This is almost 500. So from 125 to 500 microinches per second. We're quite a bit above where the lab needs to be. Our experience with ground vibration, the wavelengths that we're talking about are, could be 100 feet long. And if you can imagine a small foundation that's, 20 feet by, 10 feet, some small foundation. If the ground has a wavelength, this Rayleigh wave that sits on the top surface that has a 100-foot wavelength, that a small slab is like a dinghy. It's like a small boat. It's just going to go up and down with the waves. And you can double the size of it and make it 40 feet by whatever depth and, it's reasonable, and make it more massive. And it's still just going to go up and down with the waves. It needs to be the Queen Mary relative to the waves in order not to respond to that ground motion. So trying to do something with a slab and have it be sitting on top of the soil at this location was not going to work. The building right adjacent, I'm going to back up a slide here, a couple slides. Here's Shepherd Laboratories, another sensitive lab building that we've done work in. So there are a number of buildings here that we've done similar systems in. So we're real familiar with the geology and everything in this area. But in Shepherd's lab, we designed a similar foundation for very low vibration, maybe 15 years ago. And there we measured levels that were, maybe a little bit above 300 microinches per second. We're shooting for 125 here in this physics and nano lab. The way we got those levels, though, was to put a slab on caissons or piles that went down to bedrock. One thing that's real fortunate in this area of University of Minnesota is that there's rock that's maybe 30, 40 feet down. So it's not too hard to get down on top of that. We're shooting here for physics and nano 125. On that one, we know we got to 300. So we had to still do something different. And what our design ended up being for this was a floor structure that sat on piles. But we kept the floor structure out of contact with the soil. We kept an airspace down there. And we relied on these were big auger cast piles, the stiffness of these piles and the stiffness of the rock to give us the low vibration up here. So the ground out here is moving. This structure, our floor structure, is remaining still. And it was successful. It worked. Here is some kind of earlier FEA analysis of, you can see we've got soil, and here are the piles or the caissons, auger cast piles without the soil around it. We have a slab on top and long piles down below. This model here, even we're showing we're less than 125 in this. And here's the kind of a plan view of what was ultimately done. The red circles are the piles that went down to rock. This is approximately 120 feet by 50 feet was this clean room, this slab dimension. And the building built on separate footings and everything around it. The building is not in contact with this slab. And a picture of them putting in these cast piles.
So they can't move that equipment now.
Right.
It's a specially designed slab.
Yeah. But it works real well. It's yeah. They don't see that traffic vibration. They don't see trains. No complaints. We have been back there to measure it as well, and it meets 125. In of course, all the mechanical equipment in the building had to be isolated, and had to watch out for lots of details besides just this structure. But
how much does that increase the cost of the slab, or like? I don't know, or just roughly, like, is that?
I don't know. It was expensive. This is expensive to do. But necessary. VCE is a really difficult criterion to meet. And particularly when you're in such a congested area with trucks and traffic and everything going by, trains. If that's where it needs to be, it's probably going to be expensive. The saving thing was that the rock was not far away.
Yeah. Is VCE typically the lowest that you'd have to design to?
No, now they have FG. We had a spec that came through yesterday for G. So it's halving. So BCE is 125, D is 250, C is 500, right? B would be 1,000, A would be 2,000. So F is going to be half again what E is, right? It's difficult. It's real difficult. In this spec that came through yesterday was for a microelectronics fab, and the structure we designed there for VCE, not for VCF. They'll have to go to active vibration control to get VCF for that piece of equipment on that fab floor. This is another foundation example. I put it right after physics and nano because there's a lot of the same principles here, and I also have a plot here that shows these VC curves in a second. But this is was a new medical office building just north of.
I'm sorry to interrupt, Tony. Yeah, there was one question that came in on the U of M building. What was the thickness of the concrete slab on the drawing you showed?
Good question. So you can see between, I didn't talk much about the structural system here, but between in this north-south direction, sitting on top of the piles, there is a concrete beam, right? You can see that running this north-south direction, and then the slab sat on top of those beams, and there were purlins concrete purlins that spanned the opposite direction, the east-west direction. And I remember a number of something like 18 inches. I don't see anything here I can kind of roughly scale off of, but I recall 18 inches.
Thanks.
Sorry, I don't remember more. So we have a medical office building north of downtown St. Paul, and tenant came in and leased part of the space and wanted to put an MRI in here, MRI equipment. And the edge of the building to the center of this on-ramp was maybe 80 to 90 feet. It was fairly close, and there was a lot of truck traffic that would come down this ramp, picking up speed. And so you get a semi, maybe they're at 50 miles an hour here, but you're less than 100 feet away from where the MRI is, and we recognized this right away when they wanted us to come out and tell them whether this was a good site for this MRI. They'd already leased the space and had already started building it out when we got the call. So this is a plot that shows these VC curves. Here's VCE at 125, and the big warning that says difficult to achieve. And then VCD is at 250. Here's the numbers. C at 500, 1,000, 2,000, 4,000. MRI criteria here are usually in units of micro Gs, and it's narrow band, not 1/3 octave. But I overplotted it here just to give us a relative feel for how sensitive MRIs are to other types of equipment, and to show you these VC curves. The lowest three VC curves that are plotted here, VC C, D, and E, start at 1 hertz. It's a flat line out to 80. These other ones, from 8 hertz to 4 hertz, have a negative slope, as you can see. And then there are another family of curves that are even here that we typically call them ISO curves. And this is one that's common for operating rooms. And it goes down to 1 hertz. Kind of got a little kink in here at 4, but then there's some in here for residential and one for office. There's even a workshop one that's up here. Similarly, it's all just doubling of this flat line amplitude as you go up. And these are all VC, but not for the MRI. So we went out and they've already got the building up. They've already got this area for the MRI. They never did an infill here of the concrete because they didn't know what was going to be needed. But they put a little slab here that we could measure vibration levels on, which I'll tell you is not necessary. I'll show you in a second that whether we measured on this little 3 foot by 3 foot slab, or we measured on the dirt, or we measured on this edge of the building, or we got onto the footing of the building, we're pretty much going to get the same answer. And it's that example of that little boat in the waves I showed you a little bit ago. When the earth is moving, things that are this scale doesn't matter. They're going to go up and down for the ride. At these frequencies, these lower frequencies, they're going for a ride in that soil. And there's not a lot you're going to do about it, unless you can build the Queen Mary. So we made vibration measurements.
To attach to the metal thing, like attaching accelerometers to dirt, wouldn't that be more difficult? Or
you know, our vibration levels. So this is probably sitting here. We've probably got some wax on the bottom of it to the concrete. Our acceleration levels are not high enough that we have to mechanically fasten this with a bolt, or we have to bond it real tightly because it's not moving. The vibration levels are too low, right? So even if we went out into the dirt, we would want to get it on a nice level surface and maybe pack it down a little bit, make sure things aren't going to move around. But the amplitudes would be the same in both locations. There are some people that will drive stakes into ground, and they'll do all sorts of stuff like that to want to connect to that ground. And in my opinion, they'll start causing themselves more problems because that stake that they use to put their cell on, it might have its own natural frequency. They might introduce a problem more so than attached to the soil. We're talking about really low levels of vibration here, not high levels of vibration. So we made measurements at this site, and here is probably a truck or something coming down that ramp, or maybe down the highway, and we get this transient. And when we do an FFT on this data, here was the actual criterion for that MRI model, this red line, and here in the 12 hertz range, 12 to 14 hertz range, we've got vibration that's too high. And this is real common frequency range that we see traffic, both combination of traffic and soil. The suspensions of trucks and things tend to be in this 10 to maybe 16 hertz range, and it's not uncommon to have the soil. It just wants to vibrate at those frequencies as well. So it's not uncommon. That the highway is not smooth, and that on-ramp was not very smooth. There were bumps and potholes and cracks that vehicles were hitting. And so they were putting these impulsive forces into the ground. So there was big discussion as to what to do. Our opinion was this wasn't the best place to put an MRI. To do things, we're going to have to do some special things here. They proceeded, they excavated this area. Here you can see they even exposed the column footing back here. And we came back and made more vibration measurements. And this might not be the best data, but I think it demonstrates it. We made a measurement on, they put that little 3 by 3 slab back, 3 foot by 3 foot slab back in the middle. We measured on that slab, we measured on that column footing I just showed you, and we measured on the sidewalk outside the building. And if you look at the peak vibration level here, this is about 175 micro Gs. This is just a hair less than 175. And this one is just a hair more than 175. Now, yeah, the frequency content looks a little better, and I probably could have found some cleaner data. But, you know, it didn't matter whether I was on the building footing, if I was on that little concrete slab, or I was outside the building. It was all going pretty much the same. And again, we told them we didn't think that it was going to matter if they put a big thick slab in there or not. What they really needed to do was put an isolated slab in. And what they didn't want to spend the money on that. So they came in here and they finished this off. And this bottom of this pit is actually a 20-inch deep concrete slab. So again, that's pretty small compared to what we predict for the wavelengths of this vibration. So we came back, we made vibration measurements again, and we measured on the floor, and I don't exactly remember where it was up here, someplace on the building floor, and we measured in the center of this slab. And here's a comparison of 4 different measurements, okay? And the blue line is the isocenter, where the MRI would sit. The center of the isocenter is where the center of the MRI is, on that 20-inch slab, and the red is on the floor. And I mean, you can see that, but it's pretty much the same. These curves they match pretty well. There was not any difference in those curves. Maybe this one might be the worst, these two. And maybe the 20-inch slab is blue, and it's a little bit higher than the floor, actually. So what they ended up doing, whoops, sorry, I hit the end button rather than the down button. Sorry, gotta go. I messed up. Okay, what they ended up doing, what we designed for them then, was an isolated slab. So here's this 20-inch slab you can see here that they put in, that we measured on. We've got another mass of concrete on top of an elastomeric material. It's a special polyurethane foam material that's used for these applications. I think they flew it from Germany to get it here. It's by a company, you may be familiar with Getzner. It's called Silamer, this material. And it's a really well-engineered polyurethane foam material. Comes in a real wide range of stiffnesses. So you can kind of tailor it to your application. But we ended up to get the loading right, and to get the natural frequency of this slab low enough, we had to use it in kind of strips and in this plan view kind of arrangement. But it worked. We were able to get those amplitudes down below that criterion curve. At least well enough to low enough that the MRI operates and they don't have problems.
How did you know how to lay out those strips? Why wouldn't it just been like a carpet of it?
Pardon me?
Why wouldn't it just be like a carpet of?
Because the stiffness of the pad was just a little bit too high. So they have this range of stiffnesses or capacities for the pads, and one was a little too stiff, and the other one was a little too soft. It didn't have the capacity, the load capacity. In this stiff, if we had used it as a continuous thing, it would have been, the natural frequency would have been too high, would have been too stiff. But there is that MRI. That is the picture of that MRI in that room. So you can't even tell that it's on an isolated foundation. I don't see a joint here, but the linoleum probably spans across the joint, and it's flexible enough, it works fine. But these MRIs are very, very sensitive to vibration, and I'll show you another example. So the next 4 here are just examples of mechanical equipment isolation. And this first one is an MRI as well. Client came to us, an existing hospital, but they wanted to put an addition on. And part of that addition on the first level, kind of a basement level, was a big mechanical room. And they're putting an MRI in. Of course, they're going to put the MRI above the mechanical room, which is a bad idea, because you've got all this ductwork and piping and pumps and fans. They had big fans that were hanging from this slab, kind of over in this area. And here you've got a very, very sensitive MRI. So we said, yeah, you can do it. It's going to be expensive. This isn't that MRI. This is an MRI and an angio OR, kind of a combination that's at the Children's National Medical Center in Washington, D.C. But the reason I want to show you this, so here you've got some of our country's sickest children that come here. And if we get it wrong, here's what happens. And we worry about this. Here's an image of a head. And if there's too much vibration, what it does to the MRI, you can see it's called ghosting. Do you see this other image of a head in here? Whatever the vibration does, and I can't understand the physics and the math of how MRIs work, but they're very complicated. If the math gets a bit messed up in these transforms that are being done, it comes out, you get these ghosting images. And they can see them in bad cases, you see that right away like this. The worst that I saw was the image of the front of the face, where you could see the eyes and you could see this, the skull and the mouth and everything. And then out here by the temples, there were two more eyes, and it looked like an alien. It was really, that was the most interesting one. But this one is pretty clear too, right? So we don't want to get this wrong. We want to make sure vibration levels are low enough for this equipment. We're going to trust that the MRI manufacturers know what they're doing when they put the criteria out there. So for this model, they griped about all the isolation that was going to have to be done here. The mechanical engineer told me they spent $250,000 on isolation for the mechanical rooms. So we went back after it was built and we made vibration measurements. And right away, look this, we got really high vibration at almost 30 hertz, 29 point something, and again at 54 point something. Really, really high vibration. And we were a bit nervous at that, right? What we did, we went downstairs, and you see this little dot right here. So the ISO center, the center of that magnet, would be probably pretty close to the center of the room. And this little dot right here, this little box, that was a medical air compressor. And there it sits on the floor down there. So it's got compressors in it, and it's on nice spring isolation as part of the $250,000 that they spent, right? Everything's well isolated. But when you looked up, you could see the piping from that compressor, sending the compressed air through the hospital, nice spherical rubber isolators to, separate the equipment from the piping to control vibration going into the piping. You see this piece of threaded rod right back here. You follow that up, goes right up to the underside of the structure. There's actually a steel plate here that's on the underside of the concrete, and that's a magnetic shield for that MRI to control magnetic fields. But it's bonded right to the concrete. It's right there, and that piece of unistrut or whatever it is welded to that steel, and that threaded rod goes right up to the underside of that floor. So our guy. This is a waterfall plot of vibration data, and so there are all these different slices. Maybe they're 1 second apart, these slices, and this is newer data down here and older data up here. So we made a vibration measurement, and we had one of the facility guys go down and in this nut right here, I think it was this one, unthread that nut while we were making the vibration measurement, right? So we see the vibration, the nut went loose and that vibration went away. right? He broke that connection. Clearly that was the cause. One isolator that probably cost $30. And it would have taken the contractor, 10 minutes to put that in, was the cause of that high vibration. And I think they were happy they spent the $250, They saw the value of all those isolators in these measurements. All right, any questions on that?
I love how it's like detective work.
It is. It is.
What's causing that?
There's a lot of you have to be thinking on your feet a lot of times and trying to figure this stuff out. They're puzzles, right? All of these problems are puzzles. Here's another similar problem. This is a condominium building downtown Minneapolis. The 19th floor penthouse unit. They replaced the chillers in the mechanical room. People never had a problem with noise. They put new chillers in, and now vibration levels are just crazy high. So we got called to go down and take a look. And if we go into the ASHRAE guidelines, they say that for residences, apartments, condominiums, and living areas, NC 30, pretty good background noise level, right? 35 dBA, NC 30. So we went down there when the chillers were off. Here was the measurement. NC 30. There's the 30 curve, and there's the point of tangency right there. Turn the chillers on. NC 63. Right? You're paying all that money for the penthouse, and it's that loud. And the problem was definitely the two new chillers. They were put in without, in my opinion, were put in without any vibration isolation. Here's a very, very, very thin little rubber waffle pad that was pretty much compressed completely. That was the isolation that was put in there. These were train isolators, or train chillers, and they were not designed to have isolation, like spring isolation or air isolation or any other type of isolation. Train said these had to be on pads on the concrete. They were relying on this concrete to give them some support for these for the equipment, the lateral support, and you couldn't put a spring under here. These plates weren't really designed to take those loads. So, we had not many options. What we did then was to say, well, if what we need to do is to keep these plates relative to each other, we need to add the stiffness that would be similar to the concrete, and what we're going to have to do is grab a hold of this thing and lock it together with some structure, and then pick the whole structure up. So, here's another look. One of the things we always get is, yep, well, hey, all the compressors and everything in this equipment are isolated. Yeah, here's the isolation. It's a really hard rubber or urethane isolator with a bolt going through it. And I mean, how thin is that rubber? I mean, this is stiff stuff. It doesn't provide much for isolation, for vibration isolation, and for noise control. So what we designed was a steel structure that fit around the chiller with air mounts. So of course we had to be able to get it in the elevator to get it up to this point. So it came in pieces, everything bolted together, and then we put the air mounts in. And then when we pressurized the air mounts, they lifted the equipment off of the housekeeping pad, created this separation, and the structure kind of locked everything together and gave it the stiffness and the rigidity that the manufacturer wanted out of this, from the slab. And there's a photo of it installed. So now you can take those rubber pads after we inflated these bags, and you can, you know, there's air gap down there. You can slide that stuff in and out, not an issue. The piping had some flex in it already, and there already were spring hangers up above, so the piping and everything kind of could float a little bit. And we didn't need to lift it very far, just far enough to get the load off the rubber, right, to create an air gap down there. And it worked. The noise levels went back down to, you know, like the chillers weren't running. You know,
How often do those have to be maintained though, those air springs?
Yep, so there's two ways of doing it. You could put they could put leveling valves in here. So you're sensing the position of the vertical position of the chiller and have a valve that adds air. Yeah, because the air is going to leak out. What they do here is they come through every week or every month, and they have a pressure gauge on them. In fact, maybe you can see one right here. And then they just have a compressed air source, and they add it to bring it up to whatever they need to be at. Ryan's heard me say this before, that probably something close to 75% of the noise problems that we troubleshoot in buildings really come back to vibration, right? It's going to start from usually some mechanical source someplace, and it's the path is usually some vibration path that we need to control. And this is another example, right? They're complaining about the noise down there, but it's a vibration problem, and it's a vibration isolation problem. So the next, I just want to show you some examples of really bad vibration isolation. And you know, people will say, "Oh, we have isolators." Yep, it's the upper left corner here. Nice little. It's kind of a hard rubber mount, but boy, that bolt and that nut are not doing much to help isolate this little air compressor from what's below it. Right, the forces are going right through here. It's short circuited, and here in the lower left as well. You know, we've got some cork and rubber pad. Boy, they have 4 nuts on that one. It's, you know. The forces are going to the stiff point, right? The forces are going here. This pad is not doing anything. And it's surprising to go into buildings and have them complain about vibration or noise and find isolators that are in this condition. We're not fans of this type of a restrained isolator anyway, where these kind of two halves kind of nest inside each other. Invariably, these get bound up. Particularly, you get this under fans that are on rooftops, and up here, right, we're getting snow and ice, and the sun's beating down on the rubber in the summertime, and it's getting rusty, and it invariably is not working. But pretty bad condition.
I just
And
want to
here,
ask Tony, Lily, does Doug still come by from a Centec?
No, he doesn't.
He doesn't.
Yeah, he
So
was on our board a while ago, but
Yeah.
he's not anymore.
So when I was an undergrad, Doug from a Centec came and he showed us at PKI restrained isolators like this. And he said, when you guys get into the field, never allow anybody to ever use these. And I've spent over a decade now telling people not to do this. And it's been bold-faced in our reports, don't do this, because we go out in the field and we see these. So I'm going to reiterate Doug's wise wisdom to me and say, never ever allow your clients to use restrained spring isolators, because they're, or not restrained, the housed.
yeah, this type of a
housed like that. The restrained spring isolators can work, but not the housed ones. They never work.
Check on the ones that are in PKI.
Oh, I'm sure they're still terrible. We used to do that tour. That's the thing. Go around PKI and see how not to do noise control.
Yeah.
Here in the lower right corner, you can see this has just been, I mean, they tightened this down so much they compressed it to the point where it's failed, right? You can see the cracks. It's not just aging, it was overstressed. This is real common. We go in and we see that the springs are fully compressed. There's just, you know, they adjusted them all the way down to lift this inertia base off of the housekeeping pad, but the springs weren't stiff enough, or there's too much load, but it's been adjusted all the way down so it's compressed. Here's one that just rusted and failed. Another housed one. We went into this. This was I think it was a hospital. I hate to say this was a hospital. These next two are hospitals. And we found this vibration from, whatever frequency it was, and we had to go track it down. And if you see here, but this fan is hung from threaded rod. There's a kind of a cork and rubber isolators here, but then it's propped up off the ductwork with some 2x4s. Not the best maintenance, but the one that just has always been the worst example ever. This is inside an air handling unit in a hospital. And I was tracking down this vibration source, and I opened up the door, and here, this was a return fan in an air handling unit. And I could not believe that it was propped up on CMU blocks and 2x12s. It just blows my mind that they had been operating like that.
We won't say whose hospital that was.
I won't say where that is, but I'm not going there anytime soon. They have replaced this, but it was shocking to me, just shocking that fan was on 2x12s and CMU blocks, and it had been there for a long time. So, and here's an example of something we see all too often. Here we've got nice. This is a college science building, a chemistry building, up in the top floor, penthouse mechanical room, and there are some real sensitive. Well, there are sensitive laboratories down below where they have scales and microscopes and things, and they have inertia base back here. It's kind of hard to see, but there's spring isolators, everything done real well. But then they supported the suction side piping with a post here that goes down to the ground. So the vibration from this pump is coming this way and is going into the floor. The way it should be done is like this. That post, that support, should be on the housekeeping pad. I mean, it's just kind of common sense, right? But it's surprising how often we see that is done like this. We kind of try to encourage our clients to we can make all sorts of recommendations and we can review submittals, but invariably it doesn't necessarily get built like what's in the drawings or it's on the submittal. And it's really easy for us to walk through a building and look for the stuff because we've chased it down for many years and we know what to look for. And many times you'll find that the springs haven't been adjusted. That the inertia pad base is sitting right onto the concrete, or there's all sorts of debris under it that's short circuiting it. And one more here, very well isolated generator, but here we've got some conduit that comes into this box with unistrut going up and down. Well, geez, this generator is moving all over the place, and those forces are coming right here, right? This is a point of vibration, and if there's something sensitive nearby, you saw how that one medical air compressor caused vibration levels too high for that MRI. That's the potential here, right? That's going to cause noise and vibration from that generator someplace. This is real common to see a hanger where the spring is kind of leaning over, and things aren't aligned very well, but the rod is up against the part of the housing of the hanger, and so we've got a vibration path here that's missing it. Here's a spring on a hanger that's fully compressed. It's overloaded. Similar here, misalignment. This is actually an example of very, very good isolation. As you can see, the pipe doesn't even touch the support. It's perfect, right? Can't be any forces through there. I didn't hear any laughing. That was supposed to be a joke.
Our masks are masking it.
Okay, okay. But sometimes it's done. Perfect isolation. There you go.
They installed
Okay.
it just like we told them
That's right.
to.
Well, I went a little bit long. Oops, sorry. I went a little bit long, but any questions? Just some examples of the types of vibration projects we work on and that I thought you might find interesting.
Should we clap?
Thank you.
Thank you, Tony. This is great. During COVID times, we could do this virtually, so really appreciate it. And thanks to everybody who's participating online. Good to see you all. And if your friends missed it, we do have a recording. So, and thank you for being willing to do that.
Okay. Well, thank you.